In this lesson, we'll solve some kinematics problems using normal and tangential components. First off, let's discuss the general idea. To solve these types of problems, the first thing is to establish the n and the t axes. Don't forget, they're fixed on the path. The tangent axis acts in the direction of motion, along the tangent to the curve, of course, and the normal axis acts in toward the center of curvature, positive. Next, we can find the velocity by simply finding the derivative of the path coordinate, ds dt. We can find the tangential component of acceleration by using one of these two equations. Remember that the tangential component is representing the change in the velocity's magnitude. We can find the normal component of acceleration from this equation. It represents the change in the velocity's direction. And finally, if the path is given as a function of x, you can always find the radius of curvature of the path by using the equation you see here. All right, now we'll start to solve some problems. Here we want to determine the acceleration of this boat at the instant shown. So the first thing to do, of course, is to set up our n-t axes. T is positive in the direction of motion, and n goes toward the center of curvature of the path. Now let's determine the two components of acceleration. The tangential component, of course, is the magnitude change in the velocity vector, and that's simply this, 12 meters per second squared. And now the normal component, found from this equation. V squared, which we know at this instant, 16 squared, we divide it by the radius of curvature, which in this case happens to be 16 also, and that's in meters. Anyway, when you work this through, we get the result of 16 meters per second squared. How do we find the resultant acceleration? Well, we use Pythagorean's theorem, don't we? A is equal to the square root of its two components. We have 12 squared, and we add to it 16 squared. When you work this out, of course, you get the result of 20 meters per second squared. Realize then that the acceleration vector is going to be directed up this way. One component this way of 12 meters per second squared, and the other component this way of 16 meters per second squared. All right, now consider this problem. Here we want to determine the acceleration of the car when the time t is 3 seconds. Originally, the car has a velocity of 2 meters per second. Notice that this is giving us our increase in speed as the car moves along the curve. Well, to solve the problem, we'll first set up our n-t axes. Do you see them? They go like this, don't they? T in the positive direction of motion, and n positive toward the center of curvature. Now that they're set up, we'll first find a sub t. But that's given in the problem, isn't it? The rate of increase in the magnitude of the velocity vector. That, of course, is equal to 2 meters per second squared. And now let's find the normal component of acceleration. Well, to do that, I first have to find the velocity of the car when the time t is 3 seconds. And to pull that off, I realize that the acceleration along the curve is a constant. Consequently, I can use an equation of constant acceleration that involves velocity and time, and not position. That would be this one. If I put the data in, I get the following. V is equal to initial velocity of 2 meters per second plus our acceleration along the curve, which is that component of 2 meters per second squared, times the time, which is 3 seconds. And working this through, of course, you get an answer of 8 meters per second, our velocity. Now that we know it, acceleration in the normal direction is simply equal to our value of 8 squared divided by the radius of curvature of the path, which happens to be 10. If you work it through, you get an answer of 6.4 meters per second squared. Now that I know it, I can find the acceleration of the car by using Pythagorean's theorem. And that will give us the following. First, 2 squared, that's the a sub t component. And then finally, 6.4 squared, our a sub n component. Working this out, of course, you get the answer of 6.71 meters per second squared. And again, realize that the acceleration has 2 components, and so it won't be tangent to the path. It'll be directed somewhat like this. All right, now consider this one. Here it states that if the speed of the car is increasing at 10 meters per second squared, we want to determine the acceleration of the car at the position s equaling 20 meters. If the velocity of the car is 0, at the position s equaling 0, that is, in the initial position. Well, to solve the problem, again, we have to set up our nt axes. I think you'll agree they look like this. Now we can apply our equation for the tangential component. Now you realize that this value is simply equal to 10 meters per second squared, the change in the magnitude of the velocity vector. Next, we'll find the velocity of the car at the position s equaling 20 meters in order to find our acceleration component in the normal direction. Well, again, we have constant acceleration along the path, and therefore we can use an equation of constant acceleration to solve for velocity. This equation we need to select has to involve position, velocity, and of course acceleration, not time in this case. So this would be our choice. Applying it, we have the following. V squared is equal to the original velocity, which is 0. Of course, it's squared. Then we have plus 2 times our acceleration along the tangent axis, of course, and that's 10. Now we have our position. Final position is 20. The original position is 0. And if you work all this out, you get an answer for V, which is equal to 20 meters per second. Now that I know it, I can find a sub n, and that's simply equal to our value of 20, which we square, and we divide it by rho, which is 20. Of course, working this through, we get an answer of 20 meters per second squared. Now that we have the 2 components of acceleration, we can find the acceleration of the car. We would simply write it as the square root of 10 squared plus 20 squared. When you work it out, it comes out to be 22.4 meters per second squared. And of course, the acceleration will be directed somewhat like this, in toward the center of the curve, with the 2 components of a sub n and a sub t. All right, now let's do this one. Here we're given the velocity as a function of position, and we're asked to determine the normal and tangential components of acceleration when s is equal to 2 meters. So time is not involved in the problem. To solve it, first we'll set up our nt axes at the position of the car. Now let's discuss finding the tangential component of acceleration. Since the velocity is a function of position, we have to relate that to a sub t. Do you know the relationship? Well, it's this, isn't it? We'll substitute the data. A sub t times ds is equal to v, and we'll express that in terms of s. So it becomes s squared plus 1. And now we need dv. Do you know how to find it? Well, if the velocity is equal to s squared plus 1, I can take the derivative of this with respect to s and find the relationship between dv and ds. I simply have dv equaling 2s ds. Of course, there's nothing from this because it's a constant, so I'll put it in. 2s times ds. Here the ds will cancel on each side of the equation, and I can get a sub t. Now I need to find it at the position s equaling 2 meters, and so let me simply write that in for s. It becomes 2 squared plus 1. And of course we also have 2 times 2. If you work all this out, you get the answer. It turns out to be 20 meters per second squared. Now we'll find a sub n. And to do that, we'll simply take our v as a function of s and evaluate it at the position s equaling 2 meters. So therefore we have this being 2 squared plus 1. And of course we want to square all this. And we divide by rho, which in our problem turns out to be 25 meters. When you work it out, you get an answer of 1 meter per second squared. Therefore, the two components are specified, and the acceleration itself is actually directed like you see here. Again, directed inward toward the center of curvature, or in toward the curve. Finally, let's consider this problem. Here we want to determine the acceleration of the car at the instant shown. The car has a constant speed of 20 meters per second up the incline. To solve the problem then, we first will set up our nt axes. They look like this, and of course remember they're fixed and the car just happens to be at this location. Now we can get the acceleration in the tangent direction. Do you know what that would be? Well, it would be equal to 0, wouldn't it? And the reason, of course, is because the car is moving up the incline at a constant rate of 20 meters per second. Next, to find the acceleration in the normal direction, we first have to find the radius of curvature of the path. That requires using this equation. So we'll need to find the two derivatives that are necessary. Let me do that first. Y is equal to 0.5 times x squared. And therefore, dy dx is equal to x, and we'll evaluate that at the position x equaling 10 meters. We get an answer of 10. Finally, we have to find d squared y dx squared. And to get that, of course, we have an answer of 1. Now that we know these two terms, we can put it in our equation and complete our solution for rho. Rho is equal to, of course, on the top here in the numerator, we have 1 plus 10 squared. And all of this gets raised to the 3/2 power. And we divide it by 1, of course. Working it out, we'll get this result here. Knowing rho, we can now find a sub n. The velocity is constant, as we've stated, 20. We're squaring that, and we're going to divide it by rho, which we calculated to be 1,015. When you work this out, you get the answer of 0.394 meters per second squared. Now that we have the two components of acceleration, Pythagorean's theorem will simply state that the acceleration itself is simply equal to the normal component of acceleration, 0.394 meters per second squared. In other words, the acceleration vector will be directed upward in the positive normal direction. And so having completed the problem, we'll end our lesson.